This lecture deals with measures of mortality. In the lecture, I'm going to be discussing some common measures of mortality, including the crude death rate, the age-specific death rate, the age-adjusted death rate, and life expectancy. So how do we measure mortality? Well, when demographers are attempting to measure mortality, we want to know the force of mortality, that is, the extent to which people are able to live to their biological maximum potential. And the ability to measure that really varies according to the information we have available. Because of that, there are many measures of mortality, and each of them vary in their level of sophistication. So I'm going to start with the most basic measure, something called the crude death rate, or CDR. While it is least sophisticated, it is the most often used measure of mortality. And so it's basically equal to the total number of deaths in a given time period, typically a year, divided by the average total population, or population at mid-year. So here's the formula for the crude death rate. We're going to denote the crude death rate as M for mortality. And you can see in the formula that we have D in the numerator, and this represents basically the number of deaths in a population in some time period. And again, that's typically a year. In the denominator, we have P, which represents the total population at mid-year, the average total population in that time frame. We also typically multiply the ratio of the deaths to the mid-year population by 1,000. And this essentially just gets rid of the decimal point and eases the interpretation and makes it interpretable as a rate per 1,000. So as an illustration, suppose that we wanted to calculate the crude death rate for women in the United States in the year 2001. And suppose that we knew in that year that there were 144,970,308 women at mid-year, and 1,232,913 of them died in that year. So, in order to calculate the crude death rate, all we have to do is just divide the number of deaths by the population at mid-year. So you can see the calculations there. So I've got the number of deaths in the numerator, the mid-year population denominator, I multiply it by 1,000, and the result I get is 8.5. And so I can interpret that by saying that the mortality rate per 1,000 was just over 8 women. So you might be wondering, why do we use a mid-year population in the denominator? Well, it's because the population is something that changes and is variable at different points in time throughout some time period that we're interested in, usually like a year. So because of things like births, deaths, and migration, the size of the population can fluctuate. And so the population at mid-year is assumed to be kind of like a midpoint, an average population, an average representation of what the population is throughout the entire year. And so we often pick the population at June 30th as a representation of what the middle of the population would look like, or the average mid-year population. So why would someone want to use the crude death rate? Well, first of all, it's a very simple measure. It only requires two pieces of information. The first is just the total number of deaths, and the second is the total population. However, it should be avoided because it actually has a couple of problems with it. So one of the problems with the crude death rate is it doesn't take into account differences in the age and sex structure of the population, which could also impact death. So consider the following. It could be that the crude death rate across two different countries, or perhaps the same country over two different time points, could be entirely due to differences in the population age structure, not the force of mortality. And so as an illustration of that, consider the crude death rates in Mexico and Lithuania in the year 2000. That year, Mexico had a crude death rate of about 4 per 1,000, while Lithuania's death rate was about 11 per 1,000. Both had the same life expectancy, 72 years. However, there was a big difference in their age structures. The elderly population, that is anybody age 65 and over, only made up about 5% of the Mexican population, while it made up only 13% of Lithuania's population. And so I'm just illustrating that by this table here. So you can see Mexico basically has a crude death rate that's smaller than Lithuania's, but it also has a much smaller proportion of elderly in the population, despite having the same life expectancy at birth, that E sub 0. So is it possible that the difference in mortality is due to something other than the force of mortality? Is it possible that it's due to the age structure? Well, to answer that question, we can use a slightly more sophisticated measure of mortality, something called the age-specific death rate, or ASDR. And basically, the ASDR is sort of like a crude death rate. The difference is that it's calculated for different age groups. And so imagine that you took the crude death rate and you had some additional information on the deaths of different people at different ages and the number of those people at those different ages. And you just calculated the crude death rate separately for people within those various age ranges. And so by doing that, you can actually capture the differences in the age structure that contribute to mortality. And you can see where the rate of mortality is higher at which ages. And so to kind of start that process, we can look at the formula for the age-specific death rate. So it looks something like this. So remember that we use M to illustrate some kind of a mortality rate. And in this case, we have M with a sub n sub x subscript next to it. And so M in this case is going to be the age-specific mortality rate for people at particular age groups, right? And the subscripts sub n sub x just refer to basically the lower age limit of that age group. That's what x refers to. And then the number of years spanning that age range, which is what n refers to. And so you can see that in all three of these letters in the formula, M, D, and P, there's a sub n sub x subscript, which means basically that we're calculating deaths specifically for a different age group. We're also calculating the mid-year population specifically for a different age group, which gives us a rate of death at a specific age group. And notice that it's multiplied by 100,000, which means that it's a rate per 100,000. And so as an example of what I mean by age groups, let's say that we're interested in people between the ages of 0 and 5. So in that case, X would be 5, and because there are 6 age groups between 0 and 5, that is 0, 1, 2, 3, 4, 5, N in that case would be 6. So like the crude death rate, in the numerator of the formula we have the number of deaths in that population, but this time this is only deaths to that particular age group. And then in the denominator we have P, the average population or the mid-year population. But here this is only the mid-year population of people in that age group. And again, we're going to multiply it by some multiple of 10, in this case 100,000, just to get rid of the decimal point and ease the interpretation. Okay, so here are the steps in calculating the age-specific death rate. And I'm going to illustrate it by showing you the calculations for the data for females in the U.S. population in the year 2001. So the first step is just to list the age groups and all the different intervals that we're interested in. So basically I have age intervals including under 1, 1 to 4, 5 to 9, 10 to 14, all the way to 85 and over. Usually these are 5-year age groups, but some are a little bit smaller, some are a little bit bigger. Okay, so first what I'm going to do is I'm going to list the mid-year population in each of these age ranges. And so you can see, for example, that under 1, there were just under 2 million females under 1 years old in that year. Likewise, there were over 3 million women who were 85 or over. So in the next column, I'm going to show you the death rate specific to that age group. So for example, there were 12,091 women under the age of 1 who died. So that would be our infant mortality rate. And looking at the other extreme, there's just under about 447,998 women who are age 85 plus who died in that year. So to basically calculate the age-specific death rate, all we have to do is divide sub n d sub x, that is the deaths in the population of that age group, by sub n p sub x, which would be the mid-year population of that age group in that year. And so when we do that, we get the age-specific death rate. Now, as it appears in the table, this death rate basically has not yet been multiplied by 100,000. So we can do that. We can multiply each of those by 100,000. And that would just give us the rate of mortality per 100,000 population. Another way of taking into account the age structure of a population in its effect on mortality is to use a demographic technique called standardization. So this essentially allows you to calculate what the mortality rate would be for 2 or more countries if they had an identical age structure. That's the approach taken by the next measure that we're going to talk about, something called the age-adjusted death rate, or AADR. The age-adjusted death rate is basically calculated by taking the sum of some standard population weight, in my formula that's WS sub x, and multiplying the age-specific mortality rate. So in the formula, we have the Greek letter sigma, the capital letter sigma, which indicates the summation operation. And it basically just tells us to take the sum, or adding together, the quantities that follow. And the quantities that follow in this case are going to be WS, which is the standard weight representing the age group of some standard population, multiplied by the age-specific death rates. And when we calculate this measure, we're going to get the resulting value is going to be just a single number that represents the force of mortality in the case that a standard age structure is used. So for example, let's say that we were comparing the US population to the Egyptian population in terms of their death rate in the year 1996. And let's say that we found out that in Egypt, the crude death rate was 6.2 per thousand, while in the United States it was 8.7 per thousand. Well, is it possible that the mortality rate is actually higher in the United States than in Egypt, even though Egypt is a sort of less developed country than the United States? Or is it possible that the difference is just due to their age structures? So what we could do basically is to choose one of the age structures as a standard age structure, and then we can standardize the mortality rate specific to each age group using that age structure as a standard value. So in my example, what I'm going to do is I'm going to figure out what the Egyptian death rate would be like if it had the same age structure as that of the United States. And so essentially the age-adjusted death rate allows us to compare the death rate net of the effective age. And so although I don't show the calculations here, basically what I've done is I've calculated the age-adjusted death rate using the US age structure as a standard age structure. So I've simply weighted the age-specific death rates by the proportion of the population at different ages in the United States. And so essentially I'm sort of asking, what would the Egyptian mortality rate be if it had the same age structure as that of the United States? And so you can see that although its crude death rate is 6.2, the age-adjusted death rate, which is what the death rate would be if it had the same age structure as the US, is actually quite a bit higher. It's 15.1. And of course, the United States, the age-adjusted death rate and the crude death rate would be the same because we're using the US as a standard age structure. So there's no difference in the age-specific death rates, right? And so you can see that after we've done the standardization, we find that the US death rate is actually quite a bit lower than that of Egypt when we consider the same age structure. And in fact, it's almost twice as high in Egypt as the United States, suggesting that age structure was contributing a lot to the value of the crude death rate. So while the age-adjusted death rate takes into account the age structure in its effect on mortality, one problem with it is it doesn't provide an intuitively appealing measure of the overall mortality experience of the population. Ideally, we'd have some kind of an index that conveys information on the overall mortality experience of that population. And so what we're going to do is we're going to calculate something called life expectancy, which is that measure. And life expectancy is derived from a statistical device called a life table, which can be somewhat complex. And so as an illustration, I'm going to show you how to calculate life expectancy from a life table using data from women in the United States in the year 2001. So there's several steps involved in constructing a life table. The first is to calculate the age-specific death rate, which we've already done in one of our previous examples. So I think it's going to be quite easy to follow. So recall that when we calculated the age-specific death rate, we started by listing the age intervals. And then we listed the population at mid-year in that interval, or sub n p sub x. And we also listed the number of deaths in that interval, or sub n d sub x. So to calculate the age-specific death rate, all we did is we divided the number of deaths in the interval by the mid-year population. And so to illustrate that, here is the beginnings of our life table. So notice that like when I calculated the age-specific death rate, I just started by listing out all of the age ranges. So we have age ranges from under 1 to 1 to 4 to 5 to 9, all the way to 85 plus. Now I'm going to show the mid-year population for each of these age intervals, just like I did for the age-specific death rate. And then next, I'm going to show the number of deaths occurring to women at each of these different age ranges. And so this is just the number of deaths. And then to get the age-specific death rate, remember we just divided the column of deaths by the column of the mid-year populations, respectively. And we got the age-specific mortality rate. So these numbers should match the ones that we got in our previous example exactly, and should look familiar to you. Okay, so as a second step, what we're going to do is we're going to calculate the probability of death, or something called sub nq sub x. And that's actually calculated using a formula. So in this formula, our probability of death, or sub nq sub x, is going to be equal to the value n in the numerator, and n is just basically referring to the size of each age interval. Typically they're 5-year age intervals, although recall that some are only 1 year and some could include more than 5 years, for example like the 85 plus age range. In the numerator of the formula, and also in the denominator, we're going to multiply n by the age-specific death rate, the thing that we just calculated. Okay, but there's also some other differences in the denominator. So in the denominator, you can see that there's this value a, and a is basically just a correction factor, and this is supposed to take into account the fact that deaths at particular age ranges aren't necessarily distributed in the same way over the year. And so for most cases, a is going to equal to 0.5, indicating that deaths occur at the midway point of the interval. So the midway point is somewhere between 0 and 1, and 0.5 is exactly in between those two. And so that just basically says that for some age intervals, deaths are evenly distributed across time. But there are a few age intervals for which that's not true. So for example, we're going to use a value of 0.85 for ages under 1 because actually deaths for infants don't occur evenly throughout the year. And then for ages 1 to 4, so children between the ages of 1 and 4, deaths also don't occur evenly. We use a value of 0.60. Okay, and then I just want to note that we use a value of 1 for the highest age range. And so being a probability, 1 means that there's a 100% chance of death occurring. And so that basically that means that death will be certain at that age range. So we can take our age-specific death rates, and then we can use that formula to calculate the probability of death for each of the age ranges. And that would be these values. And so you can see that looking at people who are under 1, the value that's calculated is 0.006. So if I multiply that by 100, that's a 0.6% chance of dying for an infant female in the year 2001 in the United States. And again, notice that the probability of death is 1 or 100%, 85 plus, our highest age interval. Okay, so now the next step is to use the data that we've just created from data that are collected empirically. And what we're going to do is we're going to create a hypothetical population, and we're going to subject that population to our age schedule, or our death schedule. And so the hypothetical population starts often at a number of 100,000. That number is really arbitrary, and it's just used as a mathematical convenience. And so that number 100,000 is referred to as a radix, and that's also denoted as L sub 0. So L is going to be the number of people in our hypothetical population generally. So what we're going to do is we're going to determine the number of people who die based on the probability of death, and we're going to basically be subtracting those people out of our hypothetical population as we go. So for example, if we start with 100,000 people, and that's our first group, and we realize that the first group has about a 0.6% chance of dying. If we take the number of people in that hypothetical population, 100,000, multiply it by the probability of death, 0.006107, and if we round a little bit, we figure out that 611 of them are going to die in that age range. So basically what we can do is we can subtract them out. And then we can basically continue calculating our numbers as we have an increasingly shrinking hypothetical population that's being exposed to our mortality schedule. And this process continues until we basically reach the oldest age. So to kind of just show you what that looks like, so suppose we start with a hypothetical population of 100,000. We multiply that value by the probability of death, 0.006107. We figure out that 611 of them die. We subtract out those 611, so we're left with 99,389. We find out that 117 of them die. We subtract those out. We continue this process. We continue kind of figuring out for each age how many of them died, and we continue subtracting them out. And what we'll see is that our hypothetical population is going to get smaller and smaller and smaller as we continuously subject it to the mortality schedule that we've created from real data. So our population continues to shrink until it gets to the highest age range. in which case we're left with 43,532, and because the probability of death is 100%, or 1, everyone dies at the end. So we're left with 0, basically, people in our population after everyone's exposed to the mortality schedule. Okay, so for the next step, what we're going to do is we're going to calculate the number of person years lived for each of the age ranges. So remember that even though we have some number of people in our hypothetical age range, it's not the case that every age range is the same size, right? Some age ranges represent like 1 year, others represent 5 years, or even more. So what we're going to do basically is we're going to calculate the number of years that those people are contributing by taking into account the number of years in the age range. And so what we're going to do is we're going to calculate the number of person years lived, which is referred to as sub n, capital L sub x. And that's calculated again with the formula. And the formula tells us basically take n, which is equal to the size of the age interval. In most cases, that's 5. And we're going to multiply that value by little l sub x, which is basically just the number of people in the hypothetical population at that age interval, minus a, which is the correction factor that we used previously, and little d sub x, which is the number of people who die of the hypothetical population in that age range. I'll note that since there are no survivors at the oldest age range, the way that we calculate the person years lived for that age range is we just divide the number of people in the hypothetical population by the age-specific mortality rate for that group. So returning to our table, here's what that's going to look like. So basically what I've done is I've basically taken and multiplied the number of people in the hypothetical population at each age range by the number of years in the age range, accounting for the correction factor and the number who die. And I get basically the number of person years. And so you can see that for those who are under the age of 1, the number of person years is 99,481, while for the other extreme, those who are 85 or over, they have 301,678 person years. Okay, so the next step is basically to take the cumulative number of person years. And what we're going to do here is we're going to start with the oldest age range, and we're just going to carry over their person years. And then we're going to keep a running total, but we're going to go from the oldest group to the youngest group, so that in the end, the youngest age group is going to have the most cumulative person years at the start of life. And so here's what that's going to look like. So for the oldest age range, 85 plus, we're just going to carry over their person years. So they have 301,678 person years. Well, if we add that to the person years of the next highest group, 80 to 84, who have 257,395 person years, the sum of those two values is 559,073. And we're going to continue doing that. We're going to continue adding the number of person years to our running total to the number of person years for the next lowest age group. And so in the end, we're going to have a cumulative number of years that someone can expect to live at each age range. But notice here that those who are the youngest live the most cumulative years, while those who live in the oldest have the fewest cumulative years left. And so, for example, those who are under the age of 1 can expect to live 7,977,418 person years. So we're almost done. The last step is basically to calculate our actual measure of life expectancy, which we're going to call E sub x. And that's calculated basically by taking the cumulative person years, T sub x, and dividing it by the number of people in the hypothetical population, L sub x. And that's basically going to give us the average number of person years that somebody can expect to live at a given age range. And so again, T sub x is the cumulative person years lived for a particular age range. L sub x is the hypothetical population in that age range. And here's the calculations for that. And so basically I'm going to take the big T sub x column, divide it by the little l sub x column, do it for each one of these values respectively. And I'm going to get the life expectancy at the different age ranges. So for example, in the year 2001, women under the age of 1 could expect to live, on average, 79.8 years. So life expectancy at birth is almost 80 years for women in the year 2001 in the United States. And so we noticed that we could look at any value, and we could figure out how many more years that they can expect to live on average. And so if we look, for example, at the age range 55 to 60, we see that they can expect to live 27.7 more years on average. And so it's a very useful tool for figuring out like what is the sort of average life expectancy for different age groups. And so life expectancy is basically just a measure of the remaining years that somebody could live, given that they're at some exact age X. And so again, we can see that the life expectancy at birth is almost 80 years, 79.8. And we found that for somebody who's age 55, they can expect to live an additional 27.7 years on average. And so that concludes this lecture. So basically, there's a number of different measures of mortality. They vary in their level of sophistication. The crude death rate is really the most basic measure, although it's not particularly good at accounting for things like the age structure. The age-specific death rates and the age-adjusted death rates are much better at that, but they don't really give an intuitive sense of the overall number of years that people can be expected to live in a population, which is what we can get from getting life expectancy, which we calculate from a life table.